Quantum physics, science that challenges reality itself, where particles can vanish and reappear, exist in two places at once, and can even change when we look at them. Is it not magic? No, it is science that defies intuition at the smallest scale. It is science that is easy to understand yet hard to comprehend. This mind bending field in physics has baffled scientists even before it was born. But how did it come into existence? Quantum physics arose with challenges to classical physics, and one of the earliest challenges was the problem of the black body radiation, and it led to one of the major ideas of quantum physics, that is, quantization, measuring quantities in discrete rather than continuous units. A black body is a piece of material that radiates corresponding to its temperature, but it also reflects nothing and absorbs all the light falling on it. Thus is called black body, because the object would appear perfectly black as it absorbed all light falling on it. When you heat a black body, it would radiate, emitting light. After many attempts, no physicist was able to explain the black body spectrum until Max Planck came up with a radical suggestion. What if the amount of energy that a light wave can exchange with matter wasn't continuous, as postulated by classical physics, but discrete? This idea was quite new and shocking. What Planck was saying was that the energy of the radiating oscillators in the black body couldn't take on just any level of energy as classical physics allows. It could take on only specific quantized energy, and this was the birth of quantum physics. Sort of. It led to one of the major foundations of quantum physics. After the problem of the black body radiation, the next crisis for classical physics was the experimental results of the photoelectric effect. That is, when you shine light onto metal, you get emitted electrons. The electrons absorb the light you shine, and if they get enough energy, they're able to break free of the metal surface. According to classical physics, light is just a wave, and it can exchange any amount of energy with the metal. When you beam light on a piece of metal, the electrons in the metal should absorb the light and slowly get enough energy to be emitted from the metal. The idea was that if you were to shine more light onto the metal, the electrons should be emitted with a higher kinetic energy, and very weak light shouldn't be able to emit electrons at all, except in a matter of hours. But that is not what happened. No matter how weak the intensity of the light was, electrons were emitted as soon as someone shone light onto electrons. This was because the kinetic energy of the electrons was dependent only on the frequency rather than the intensity of the light. The results were hard to explain, at least classically. Then Einstein came in. Inspired by Planck, he proposed that light was also quantized just like energy. This idea later contributed to the development of the wave-particle duality. The wave-particle duality was discovered by Louis de Broglie, who suggested that not only did waves exhibit particle-like aspects, but the reverse was also true, which was that all material particles should display wave-like properties. And the fact that waves exhibit wave-like properties gave rise to more trouble, but also inspired Werner Heisenberg to come up with the famous uncertainty principle, also known as the Heisenberg's uncertainty principle, that says there is an inherent uncertainty in the relation between position and momentum, which basically means that the more accurately you know the position of a particle, the less accurately you know the momentum, and vice versa. Heisenberg's uncertainty principle is a direct consequence of the wave-like nature of matter, as a wave can't be completely pinned down, Later contributions to the field involved the Schrödinger equation that describes how the quantum state of a system evolves over time and is a fundamental in quantum mechanics, just like the Newton's laws in classical mechanics, and quantum electrodynamics, developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. And this describes how light and matter interact using quantum field theory, which was also introduced by Richard Feynman, but included other physicists like Paul Dirac, and led to major discoveries like the Dirac notation, also known as the Bra-Ket notation, that predicts the existence of antimatter and the Higgs mechanism, leading to the discovery of the Higgs boson. Quantum physics is still developing actively, with major breakthroughs happening even today. Some instances would be China's Mikias satellite that successfully sent entangled photons over 1200 km that could lead to a global quantum network and hack-proof communication, and the ultra-precise atomic clocks, which are 100 times more accurate than existing ones. There has also been a new emerging field in quantum physics, the field of quantum biology, that applies to biological processes and could lead to a better understanding of diseases linked to enzyme dysfunction, genetic diseases, and might even change our understanding of biology. This was a short history on quantum physics. If you enjoyed the video, don't forget to like, share, and subscribe to our channel for more content on quantum physics, as in the future we will be discussing some of the foundations of quantum physics as well as some of the advanced topics.